So this is just a quick overview of what we've done in class over the last couple of days, particularly on the area of microcontrol. We have been looking at the advantages and disadvantages of the use of microcontrol, what microcontrol is in itself, being able to create basic flow charts that look similar to what you've done in maths, look at the terms of a bit pattern and byte, and also looking at the term binary and counting. But it's binary and counting that you probably need a little bit of information face to face instead of just over a tutorial like this. So what we already know is what the use of a time constant, a capacitor and a resistor. In its basic form, as the capacitor fills up, the transistor will then switch on. We then modified the same time constant but added in a 555. So the advantages of 555 over a transistor was accuracy, but also in monostable and astable it had the ability, using pin 7, to discharge the capacitor as well as charge it, whereas over in the normal transistor circuit we would have had to put in a push to make switch. So today's lesson is not looking at 555, but it's now taking a step on to what is next, to take the next step of advantages. So from the advantages of transistor through to the advantages of 555, that brings us out now onto a new area which is known as PIC. So PIC is a microchip, just like a 555, but this time we will be using one that is known as a Genie 18 or E18, one that has 18 pins, 9 either side. So don't worry how many pins I have here, but if we even take the analogy of one is positive and one is negative, we then would have inputs over on the left hand side and we would have outputs over on the right hand side here. So there are many advantages of using a PIC chip. The main one is that it's programmable, so we can actually program a flow chart onto and download onto the PIC chip. That also means that we can reprogram it as well if we find some issues with it. It has multiple inputs, whereas 555 had one input in pin 2 and one output at pin 3. The main other issue or advantage is the fact that we don't need to worry about other key components. So in 555 we needed to have a capacitor and resistor to create a time delay. Here it is all based around the flow chart itself, how we program it, and we do not need to worry about the key components such as capacitor. But there are some disadvantages, not as many, but there are some disadvantages with using a PIC chip, a programmable chip. The first one being cost. It does cost more, but the second one is fault finding. With 555 it was easy to find the fault. It was only within the chip or the capacitor. Here it could be within the actual chip itself, or it could be in the wiring, it could be in the circuit. So finding faults now lies in both the flow chart that we create and in the chip itself. So what is a PIC chip? It is an integrated circuit that is programmable. One that has outputs, and I say we have them over on the right hand side here, and one that is inputs, and we have them over here on the left hand side, just to make a circuit as easy as possible. The first confusing thing with microcontrol such as PIC is the way that they number their outputs. So you can see that there are 8 dashes on the right hand side. It would be sensible to start at 1 and work our way up to 8, but instead they have started with 0 and they make their way up to 7, but there are 8 outputs. So it gets confusing when we're describing the first input and it is 0. The second thing is that when they want to label at an output, you can't use the letter O because it looks like a 0. So we start talking about Q as output, and for example Q0. And on the left hand side, these are all our inputs. We don't use I for input because it looks like a 1, but they are numbered in a similar way: 1, 2, 3, 4, 5, 6 and 7. and instead they will have a D in front of it. Now the D stands for digital. A digital logic can be one of two things. You can either press the push to make switch or not. It is seen as a logic of a 1 or a 0. So whenever I take the terminology digital, I mean 1 or 0. That would be micro switches, read switches, push to make switches, push to break switches, toggle switches, etc. Outputs here, if I take just another drawing and just concentrate on two of these, that is Q0 and Q1. I could come across and put my resistor and then into an LED. So I could have two of those, excuse the drawing, but I have two LEDs, and let's call it LED 1 and LED 2. LED 1 is connected to Q0. LED 2 is connected to Q1. So that's the first confusion that we have. So if I want to control that LED, the first thing I do is I write a flow chart. Just like what you may have learnt in maths, the first command is start. I need to tell the computer program to go to this place first. Again, the drawing of these will need to be neater than me using my finger on an iPad. But then the next one is a rectangle with very pointy corners, and that's important. Because this is a universal language, it's going to cross between different physical languages. We need to have a standard. So a rectangle is going to take those outputs of my PIC chip, all those 8 dashes. And I'm looking at Q0 and I'm looking at Q1. So if I wanted to put the first LED on, the one at Q0, what I maybe write inside, just for my own understanding, I will write LED 1 on. However, the coding inside that must indicate that I want to switch on this output here. And it is written in this format. So we have to write it as a code, and we start with what's known as the LSB, the least significant bit. So earlier on I talked about a digital being a 1 or a 0, and one of these codes on their own is known as a bit. And then we take the least significant bit is Q0. So I'm not going to write the letter Q in each one, but if you can follow along. So then I go from right to left, output 1, 2, 3, 4, 5, 6, and 7. So if I wanted to light up the first LED, I want to control it with this code. And if I only want to light it up, I put a 1 at Q0 and everything else is switched off. So my code becomes 0000 0001. Which leads me on to the name that we give all of this. One individual number is known as a bit. 8 of those numbers is known as a byte. But we can also classify this code, all the string of numbers, as a bit pattern. A bit pattern is used to control the outputs that I'm pointing at now on here. So if I wanted only Q01, it would be 1, 0, 0, 0, 0, 0, 0, 0. If I wanted them all on, I would write a code of 1, 1, 1, 1, 1, 1, 1, 1. And that would mean that I'm seeing 1, 1, 1, 1, 1, 1, 1, 1. If I wanted Q1 to be on, this one here on its own, it would be 0, 0, 0, 0, which is here, 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 and here. And the next one would be 0, 0, 1, because I want this one on, which is here, and this one off. 0, 0, 1, 0. So this is classified as a bit pattern, and it controls everything that we have on the right hand side of a PIC. So a bit pattern, whatever code I want. So for example, if I had multiple LEDs and I had 1, 1, 0, 1, 1, 1, 0, 1, I would be controlling the top one, the second one, the fourth one, this is from the top down, and the next two, miss one, and there. All of the ones highlighted in red would be on, off, on, off, on, starting with the least significant bit, and the least significant bit is Q0, and we work our way across. So what does that look like in a flow chart? So I want to have LED 1 on only, so I would go 1, 0, 0, 0, 0, 0, 0, 0. There are 8 of them because there are 8 outputs. I want to keep that LED on for 2 seconds. So the code that we use is a rectangle with slightly curved corners, and inside says the word wait. And the wait cell is measured in seconds. So if I say wait 2, it's going to hold my LED on for 2 seconds. After 2 seconds, I want my second LED to come on as well as the first one. So take another rectangle, pointy corners, it's an output, LED 2 on, and the code would be 0, 0, 0, 0, 0, 0, 1, 1 for LED 1 and LED 2. And then we take another wait if we want to keep it on for 2 seconds, so wait 2. And then I'm going to put all LEDs off. So all off. And the code will be 0, 0, 0, 0, 0, 0, 0, 0. And then let's stop the program with a stop. So that's all we did in class, was a basic program looking at it as a flow chart, starting to understand symbols. So the code, the universal code, is the actual symbol shape. So a symbol of a rectangle with very curved ends is a start and a stop cell. Rectangles with pointy corners are outputs, which then are attached with a code to tell you which one to switch on and off. The label inside is only for our understanding. A wait cell holds the original cell, the previous cell, on or off for a period of time, and then we can progress down until we stop. The only other area that we started to look at was looking then at the input cells. So we had on the left hand side 1, 2, 3, 4, 5, 6, 7, 8. And again, let's take it as least significant bit 1, 2, 3, 4, 5, 6, and 7. 7 different cells. If I had a push to make switch, I'm going to highlight it here. If I had a push to make switch here, and whenever I press the push to make switch, I want to have the signal going high. So it's going to have a logic of 1. So whenever I press the push to make switch, there's going to be a 1 here. The way that the program will sense that is just like in maths. I think you call it an if cell, and we use a diamond shape, and we have the yes and the no outputs within that. So if the push to make switch is pressed, it goes to yes. And inside the code will write if the push to make switch is pressed, least significant bit on the right hand side, so a 1 because the push to make switch at Q0, D0 is pressed and nothing else pressed, so my code is going to look like this, my bit pattern. So the question is the push to make pressed or on? How do I know? Because it will send a logic of a bit of a 1 at Q0, or sorry, not Q0, D0. So we call this a digital cell. It's also known as a decision cell, but it is making a decision based on what the input will be. So if the input is not pressed, it is not a 1, and therefore the question is it a 1? It is not. It goes back up to no and goes back round to ask the question again. So whenever you were counting in primary school, you will have been taught one of 10 different number values. And you can see them being written, nothing new here. But at this point, I don't expect you to understand all of this over a screen, so do come back down and speak to me. But if I wanted to write the number, so this is not necessarily counting yet, but just simply displaying a number on a page, if I wanted to write the number 102, I can use anything from the digits that I've been taught, so 1, 0 and 2. If I wanted 300, I could go 300. If I wanted 340, all the numbers are there for me to use. It is known as decimal because the word dec means 10. Excuse the terrible drawing of a hand, but if I wanted to count in primary school, you're encouraged to use your thumb, and then for 2, you use your index finger and thumb, keep them up. Middle finger for 3, so count 1, 2, 3 up, and then 4 is your ring finger, and then your little finger. So if I wanted to count to 5, I would have all fingers up. If I wanted nothing counted, none were up. So every time I count, I add 1 on, and that's how you are counting in decimal. But the problem arises whenever we are using decimal for counting, we soon run out of storage. So as I use each digit, I can only count to 5, and then I use a second hand. But I'm limited by the amount of values that I have. It's slow, and it is heavy on file storage. So a new way of counting is using digital or binary as it's known. So we should now know that the word digital means 1 or a 0, which means instead of having a list of 10 digits to use, all I have in my itinerary is a 0 and a 1. So if I wanted to write 12, I can't write it in my normal format because I only have a 0 and a 1. And the way that that the binary is used is I go for the LSB, the least significant bit. So let's go for the little finger here, and let's go for 1, least significant bit. The ring finger being 2, then, sorry, not 3, 4. It doubles up each time, and you'll see the pattern arising here. So 4, 8, and 16. Looking at only 5 digits. So if I did this and I switched all of those off, the answer is 0 because there's nothing on. If I had one finger up at the number 1, then I count the total value of all the 1-ons, and that in this case is 1. If I wanted to record the number 2, it would be a 1 at 2 and all the rest off. If I wanted 3, I have the 2 and the 1 on. I count the total value of each one that is on. If I wanted 4, it's 0, 0, 1, 0, 0. If I wanted 5, it is 0, 0, 4's on, 2's off, and 1's on. 4 and 1 make 5. If I wanted 16, it would be a 1, 0, 0, 0, 0. If I wanted 31, 31 would be 16 plus 8 plus 4 plus 2 plus 1. So a way of counting, instead of using a hand which only can count to 5, all of a sudden I can count to 31 in one hand by using a slightly different counting system. A system that only uses a 0 or a 1, but whenever I write it out and I had my 0, 0, 0, 1, 0, instead of it being the answer of 10, that actually is the second one on, which is 2. So this answer equals 2. So just to finish, there are 2 different places where you see a bit pattern. You can see 0, 0, 0, 0, 0, 0, 1, 0, and that could be to switch on an LED whenever I'm looking at outputs. I could also see 0, 0, 0, 0, 0, 0, 0, 1, and it could be looking at inputs and asking the question, has the push to make switch been pressed? And place that you can find it is if I write 0, 0, 0, 0, 0, 1, 1, 0. Here, the least significant bit forward, this answer is 2 and 4 together, which equals 6 in decimal. I don't expect you to pick that up just over a screen. Do call down to see me, but hopefully that gives you a little bit of an overview as to what we're doing. So recap, we have got a pick chip, which is a programmable, which we add in a flow chart, which then needs to have a bit or a byte or a bit pattern to make it work. to code it properly, which uses symbols, and then we also looked at being able to count in binary. Okay, talks about